So in the last video we had talked about the system stability and we had just gone through the basics of the Routh's criteria, and we had also found out the Routh's criteria is not the one and only criteria that we need to see for the stability of a system. It is definitely a necessary criteria, but it is not a sufficient criteria. So we needed a sufficient criteria that would serve the purpose. That criteria is the Routh-Hurwitz criteria. It starts with the same thing that we need to find out the characteristics equation of a system. Let us suppose any random characteristics equation. Okay, suppose we get this characteristics equation as 3s to the power 4 plus 2s cubed plus s square plus 4s plus 4 equals 0. Right. So looking at it, it definitely appears that it satisfies Routh's criteria because it has all the powers of s and it is also positive. Now let us see what Routh-Hurwitz criteria tells us. Routh-Hurwitz criteria tells us that first we have to make a matrix out of this thing. How do we make the matrix? The matrix is to be made such that there will be, if there are the highest power of s is 4, there will be 5 rows in this matrix, starting from s to the power 4, s to the power 3, s to the power 2, s to the power 1, and definitely s to the power 0. Okay. The first row will be filled up with the coefficients of, first of all, the highest power, that is s to the power 4, and then an alternate powers, that is s to the power 4 if it is first, then we'll not take the s to the power 3 term, we'll directly go to the s square term, that is we'll take the alternate powers in the first row. So here s square, it's 1, then we'll not take the s again, we'll go to the next s to the power 0 term, that is 4, right? But so what will happen to the alternate terms? This will go on to the next line, that is the missing term, that is this 2 out here and this 4 out here. Where there is nothing, there will be 0 definitely. Now we can find out the first 2 rows with the help of this. We need to find out all the rows. Okay, how to find out all the rows? We all know about matrix determinant finding. This process in Routh-Hurwitz is almost similar to matrix determinant solving. What do we do in matrix determinant? We multiply this into this and then subtract this into this. Here we do the opposite. First we do this into this and then subtract this into this. So what we'll do is 2 into 1 minus of 3 into 4, right? And we'll divide it by the first digit of the previous row, that is 2 out here. This will be the first column. Okay, the next column, definitely what would it become? The next column, it would become, we have to do the same action, keeping constant the first row and just changing this row. First we did this into this and then minus of 3 into 4. This time we'll have to do 4 into 2 minus of 3 into 0. We'll keep this row as a fixed row and we'll just move on we'll just move on another column behind. So this will be 2 into 4, that is 8, minus 3 into 0, that is 0. So 8 by 2, which gives me just a 4. And here let's calculate what this is. This is 2 minus 12, that is minus 10 by 2, that is this equals minus 5, right? Minus 5. And then s to the power 1 row, this will be again these action, minus 5 into 4, that is minus 20, minus 8, minus 20 into minus 8, then plus minus 8, that is minus 28 by minus 5, that is minus 28 by 5, that's almost equal to 5.6, right? And here what we get here, this would be a 0 row because minus 5 is 0 and 2 is 0, that is a 0. And the last row, that is 5.6 into 4 minus 0 and minus 5 by 5.6 just gives me 4 because this whole thing is 0, and 5.6 into 4 divided by 5.6 gives me 4. So we have find out the matrix. Let me write the matrix in a better way again. This is 3 1 4 2 4 0 minus 5 4 0 5.6 0 0 and 4 s to the power 4 s cube s square s to the power 1 and s to the power 0. So this is the Routh-Hurwitz matrix that we have found out. Now, what conclusion can we make of it? We only need to observe the first column of the matrix, and the number of sign changes in the first column of the matrix will be equal to the number of poles on the right half of the S plane. Keep this in mind, that is, the number of sign changes will be equal to the number of poles on the right half of the S plane. Here, positive, positive, no sign change, positive to negative, sign change 1, negative to positive, sign change 2, then positive to positive, no sign change. So there are two sign changes out here. So there are two poles on the right half of the S plane. So is this system stable? It's definitely not a stable system because there are two poles on right half, right? So we can see that although it was satisfying the Routh criteria, it is not satisfying the Routh-Hurwith criteria, and so system is not stable. System is not stable. So that is what we get from Routh-Hurwith criteria. In the next video, we'll be doing one or two more typical examples of Routh-Hurwith criteria. Thank you for watching.